The next hydrocarbons are alkynes. Alkynes, we know that they have a general formula of CnH2n minus 2. They are the organic compounds or hydrocarbons which contains at least one C triple bond. Now they have a triple bond, that means the two pi bonds are present along with the normal sigma bond, and that makes it a triple bond. What is most important to note in this is that they are commonly called acetylenes or the derivatives, because an acetylene is the first alkyne which we have is C2H2. Now let us see first their nomenclature. See, we know that we call them alkynes, and if we have suppose CH3, C triple bond, C, CH2, CH3, we will call it what? Pent 2-ine. And remember, yes, if we have suppose this kind of a branching, we will give preference to this triple bond, because definitely we know that this is a sort of a functional group, so it has to be given a higher preference. So we'll start our numbering from this side, so it will be 3 methyl but 1-ine. So that's the same thing here. Then let us see the isomerism shown by the alkynes. Now they show two types of isomerism, both chain and position isomerism. How we can see this one? This is yours hex 1-ine. And if we have this one, this is hex 2-ine. So this is hex 1-ine and hex 2-ine, they shows position isomerism. Whereas, because the position of the double triple bond has been changed. Whereas if I draw it like this, this one, what we find is this is the chain isomer of the first one, because the position of the double bond hasn't been changed, it's kept at carbon number 1, but the chain now is of 5 carbon in place of 6 carbon. That's why we call it a 4-methyl pent 1-ine. So this is 4-methyl pent 1-ine. So this is what we have the different types of isomerism in case of alkynes. Let us see the structure of a triple bond containing hydrocarbon. Remember, whenever we have two carbon which are actually forming a triple bond, we know that basically their px and py orbitals, they both are getting what? Sideway overlapped. As a result, what happens is, what we find is these are the two hydrogens they are having already. So this is a sigma bond, this is a sigma bond, this is a sigma bond, but these two are the pi bonds. Now that makes this molecule to be appearing like this, in which this is a sigma bond and these are the two pi bonds. Now due to this triple bond, the two carbon comes more closer to each other, and that's why this bond length is 1.20 Angstroms unit. I'm talking about Cc bond length. Also, the carbon's electronegativity gets much more increased, because now both of these carbons are sp hybridized, and as a result this angle is between them is 180 degree. Now the most important question, out of alkenes and alkynes, which is more reactive? We know that alkenes are more reactive. We often get confused in this, we often get misguided that why the alkynes are lesser reactive in spite of having two pi bonds. So there has to be much more electron density in this case, but it's not like this. The reason is because what happens is, these two carbons which are actually showing overlapping of the two px and py orbitals, they almost require a barrel shaped sort of electronic clouds around them. It becomes almost a hollow cylinder, at the center of which we are having the two hydrogens with the two carbons with the hydrogens. Now that's why what we find, there is more delocalization of the pi electron, and as a result, due to this more delocalization of pi electron, due to the sideway overlapping of both px and py orbitals, the electron density available is far less than what in comparison to alkenes. That's why alkynes are lesser reactive than alkenes. Now let us see the preparation of alkynes. The first preparation is from calcium carbide. Calcium carbide, when actually reacted with water, it results in the formation of calcium hydroxides like lime and your acetylene. A very important industrial method of preparing the alkynes. We need to know how we get calcium carbide. Calcium carbonate, when the lime is heated, we get calcium oxide, quicklime and carbon dioxide. This quicklime is when heated with coke, we get what? Calcium carbide, mainly by this process. Of course, the side product is carbon monoxide, and this calcium carbide, when actually reacted with water, it gives us acetylene gas. The second method of preparing alkynes is from vicinal dihalides. This is again by dehydrohalogenation. So if we have this type of vicinal dihalide like 1,2-dichloropropane, and we react this with alcoholic KOH, we need to know this. For this chlorine, this is the beta carbon from which the hydrogen can come, and from this chlorine, this is the beta carbon or beta hydrogen available from this carbon. That's why what happens is, due to the two dehydrohalogenation takes place simultaneously, what we get is this alkyne plus of course KCl plus H2 and this as a byproduct. So this is how we get higher alkynes prop 1 ine. Now let us see the properties of alkynes, and in this we will see first the physical properties. See, their state is C2 to C4 are gases, C5 to C12 are your liquids, and C13 or above are the solids. See, these are colorless compounds, maybe the gases, solids or liquids. Their other properties are very similar to alkanes and alkenes. They are very, very less reactive in nature. Their melting points and boiling points gets increased with the increase in the number of carbon atoms. Since they doesn't show any type of the stereoisomerism, so we can't have cis trans or sort of things or differentiation. But what we find is, yes, they are again, solubility is also very similar to other two hydrocarbons. They are soluble in the organic non-polar solvents like benzene, CCl4, etc., but insoluble in the polar mediums like water, etc. Then let us see the chemical properties of alkynes. The first in the list is the acidic nature of alkynes. See, we need to know, due to the more S character in the sp hybridized triple bonded carbon atom, the CH bond is highly polar in nature. That is why when any alkyne like this one is reacted with sodium, or we can react this with soda lime or sodamide, what we get is this NH2 replaces, or sodium replaces this hydrogen, which is the most acidic one we are having, and what we get is your C negative Na plus sodium acetylide, of course with ammonia as a byproduct. Now on this sodium acetylide formed, what happens is, this becomes your nucleophile. You can react this with any of the alkyl halides on which it attacks as a nucleophile, substitutes bromine out, and what ultimately we get is this whole group gets bonded to this chain. And what is the product obtained out of this is, let me write down here, it will be CH3C triple bond, and this carbon chain of the alkyl halide gets attached to this in place of this hydrogen or sodium. So what we get is a higher alkyne, which is your spent to ine, plus of course we get NABR. So this is a reaction which not only shows the acidic nature of the CH bond or of the sp hybridized triple bonded carbon atom, it also leads to the formation of what? Higher alkynes. The next reaction of alkynes are the addition reactions. We know that they are having a triple bond, 2 pi bonds are there. So we can add 2 molecules of hydrogen or halogen acids or even halogens, even water also, and that is what makes them different, is that they mainly show the additional reactions. Most of their additional reactions are electrophilic additional reactions, and in unsymmetrical alkynes simply the Markovnikov's rule is followed. Let us see first the addition of dihydrogen, which is also called hydrogenation. We can take any alkyne and we can add hydrogen in presence of platinum or palladium or rancenical, and this gives us first the alkene, and when repeated this reaction again, this gives us alkyne. Or if we leave this system with these catalysts, what we get is the product obtained is alkane. So ultimately propane is obtained from propyne, and this is what is called the addition of 2 molecules of hydrogen to this alkyne is called hydrogenation, and we get alkanes out of it. Then let us see the addition of halogens. See, if the halogens are added to any alkyne like this, like if we are taking bromine in CCl4, what we get is C, Br, Br, CH, Br and Br. So what we get is 1, 1, 2, 2, tetra, bromopropane. So what we get is that 2 molecules of bromine actually are added to this alkyne, and 1, 1, 2, 2, the tetra halo products are obtained on addition. And what we find is the orange red color of the bromine also gets decolorized, which is again is a test to check the presence of the alkyne or unsaturation in the organic compound. Now let us see the addition of halogen acids. The addition of halogen acids follows Markovnikov's rule, where if the alkyne is unsymmetrical. Let us discuss this particular example, propyne, which is an unsymmetrical one. When this is reacted with HBr, what we find is, as per Markovnikov's rule, the negative part will go to the more substituted carbon, or with the carbon which is having lesser number of hydrogen atoms. So what we get is, we get this product. So the product obtained is 2-bromopropene. Now on this, one more molecule of HBr is being added, or it itself gets added because there is an unsaturation still available. Now again the Markovnikov's rule will be followed, and therefore the bromine will go to the same carbon which is having already one bromine. So what is the end product is, what we get are gem dihalides. So we get gem dihalides. Gem dihalides are those alkyl halides on which the 2 halogen atoms are present on the same carbon atom. So that's why they are gem dihalides. So it will be 2,2-dibromopropane, the product is obtained, and this is what is the addition of halogen acids we are having. Now let us discuss the addition of water. Which is also called hydration. Now whenever water is added to alkyne, it has to be done in the acidic medium. The reason being, we need a proton in order to which act as an electrophile, and which can actually lead to the breaking of the triple bond, one of the pi bonds out of the triple bond by the electromagnetic effect, and as a result water as a nucleophile attacks. Now the product obtained in this case is this. Of course the water will OH, a negative nucleophile will go to the carbon which is more substituted and having lesser hydrogen as per Markovnikov's rule. So what we get is OH here and a double bond and a CH2 group. Now this is the enol we have, this particular compound. Because why enol? Because the carbon which is having a double bond is also having an OH group. Now this one undergoes tautomerism. The migration of the hydrogen takes place, and this gives us what? The propanone. So what we get is acetone or propanone as the product of hydration of alkyne. Don't ever think that the reaction will stop here. This product will automatically automerize to give you the aldehyde or a ketone. We can take one more example. If suppose we are having the acetylene, and if we add water to this in acidic medium, remember we do this addition in presence of mercury sulfate. Remember we do this addition in presence of mercury sulfate. Now when this, in presence of it, when the water is added to acetylene, the product obtained, the reason being is acetaldehyde, because we know that we get though enol in this, but this enol gets shifted to this by tautomerism, and the main product obtained is your ethanol as the acetaldehyde, and it's not the enol, and these are the additional products of alkynes or due to the addition of water. Now let us see, it's another addition reaction which is very interesting, which is basically is a polymerization reaction. Yes, polymerization in case of alkynes is an additional reaction because one out of the two pi bonds is broken down. So what happens is when this acetylene is actually subjected to polymerization, many such molecules like of this acetylene, they can actually form this type of compound, this type of chain, which is called polyacetylene, or we also call them polyenes or polyacetylene. Now these polyacetylenes, they are very they can conduct electricity. The reason being because of the presence of the pi electrons, which gets completely delocalized throughout the chain, and that's why they can act as a very good conductors, electrodes for batteries, and which are much cheaper and lighter in weight than the normal metals. So that's the sort of a linear polymerization which is giving us this kind of a product. So we call it a linear polymerization. We also have its cyclic polymerization. In cyclic polymerization, what we find is the acetylene, when subjected or when it is passed through a red hot copper or iron tube, what we get is we get benzene. This is sort of a Diels-Alder reaction. What we find in this case is like this is the 3 units we have of the acetylene. So basically the 3 molecules gets involved in it. Now what happens is in these 3 acetylene molecules, the homolytic fission of the one of the pi bonds takes place like this due to extensive heat. Now the pi bond which breaks, and these free electrons or the free radicals which are forms the normal sigma bond between these carbons, and this leads to the formation of a structure like this, where what we have is these carbons still having one pi bond and the other having sigma bonds, and this is how they get connected and the benzene is formed. So that's a very important reaction, and especially from the conversion point of view, that we can get benzene, yes, out of acetylene on cyclic polymerization.